Okay, so my name is Saleem Rao and I will talk about introduction to quantum information and computing. So basically I organized this lecture in a way to give you some idea. So basic idea of behind this lecture is okay, how different this field is as compared to the existing technology. Of course, the most important kind of technology nowadays in information field of information science and information technology is semiconducting technology. Okay, you have your mobile phone, your computer, okay, internet, everything is okay, automation in automatic cars everywhere, it's a semiconducting industry. Okay, the semiconductor is the science behind okay the revolution in last 50 years, okay, different types of technology, and one of the most important part okay is the classical computers. So now the question, many students have this idea, okay, or they would like to learn if they are electrical engineers, they have a good background in classical computing. So can they switch to the quantum information processing or quantum computing? So that's basically my today's target is. Particularly, I hope all of you know the quantum mechanics is not a new theory. Okay, it's almost how much old? Any idea? 100 years. It's almost more than 100 years. So the big question arises over here. So if it is 100 years old concepts, okay, on theory was proposed early 20th century. One of the big breakthrough is photoelectric effect by Einstein in 1905, and there is a lot of development in first 20 years of 20th century. And in 1922 from Schrodinger, from Heisenberg, you have almost the quantum mechanics is mature enough, or I should say the most of the mathematical model was available to physicists, okay, somewhere around 1930. So the question is this, it's almost 100 years, 95 to 100 years, okay, you have a theory, you know what is happening. So why there is a too much delay, okay, in having the quantum computer? Anyone has any idea? Yes. Existence of right hardware, yes. Okay, yes, anyway, whatever you have in your mind, so I will just simply okay tune my okay this discussion accordingly. Okay, yes. Okay, that's good. You mean all of you have some idea about it, or you're reading, or you are just simply involved in such kind of activity. Anyone would like to contribute anything else in it? Moore's law. Okay. Now I'm going to, yeah, that's exactly as I said, my talk is okay around this particular topic. Okay, why we waited for 100 years? What was the reasons? And uh, so why it's too late? So there are a few things exactly. Some of you mentioned it. The first important thing is quantum mechanics. That's a major part of the today's talk is okay. What is quantum mechanics is? Okay, why we need a quantum mechanics, why the scientists thought about the quantum mechanics okay in early 20th century or late 19th century. Okay, so then if we have the theory, okay, why the idea of the quantum computing is too late, almost 70-80 years after having the quantum mechanics. So basically there are few experiments which I'm quite sure all of you heard about it. and you were not able to explain it by classical mechanics like photoelectric effect. Okay, another thing is the specific heat capacity. In physics 101, 102, or I can general term, I can use the black body radiation, but I will not use this particular term. You know, specific heat capacity of the water is 4180 or 4200, isn't it? We are using it in physics 102 to solve the numerical problems. But when the scientists repeated this experiment at very low temperature, what they observe, specific heat capacity is not only a property of a material, it is a function of temperature as well. So they were surprised. Okay, for years they know specific heat capacity is a property of a material. When you go to the low temperature, they observe specific heat capacity is a function of temperature as well. Very simple example I can give. I don't want to go to the detail, very complicated mathematics in today's talk, because you don't need it for quantum computing. For example, if you park your car in sunlight, okay, and so it's very common problem. Okay, and many places there is no shaded parking, you park it. And if you, when you come back after 1 hour, 2 hours, something like this, so you can see the different parts of the car body, particularly inside as well, so they are at different temperatures. Particularly in an old car, sometimes steering is too hot, isn't it? You cannot touch it. But nowadays there is all these issues. Okay, your dashboard and your steering is not very hot. So the question is, the whole car is parked under the same sunlight. Why different parts of the car, okay, are at different temperature? So it's mean very simple thing is different parts are absorbing different amount of energy. So question is, why they are absorbing different amount of energies? You are giving same amount of energy to them, they are absorbing different amount of energy. Okay, so this was the big question. You were not able to explain it by classical mechanics. Okay, another important problem is the orbital motion of the electron around the nucleus. Okay, so this is well known in chemistry, and all the chemical reactions based upon these orbital motion of the electron. You see in the electron in first orbit, second orbit, third orbit, and the chemistry is satisfy, okay, this particular model, and based upon this model, okay, you are developing a lot of things around you, lot of chemical reactions are going around it. But if you try to explain the motion of the electron around the nucleus like planetary motion, okay, just like as you know, the earth is moving around the sun, moon is around the earth, and you have a lot of, okay, artificial satellites also. So when you apply this theory, okay, onto an atom, you are not able to explain, okay, why electrons can be in a specific orbit. So these are the fundamental questions, okay, are around you, and you are not able to explain these common observation, common thing which you are observing in your everyday life. So these two processes, black body radiation, okay, or atomic structure, you are not able to explain it using classical mechanics. So you introduce the quantum mechanics over here. So basically first 20-30 years, okay, you try to explain what is happening around you, okay, using the quantum mechanics. Okay, but next question is, quantum computing idea, okay, was first time proposed somewhere in late 50s or early 60s. Feynman said this classical computer, think about it, what was the level of the classical computer in late 50s and early 60s. But those who are working on the theory side, they knew whenever this machine will be available to you, it has a certain limitation. So Feynman said it is difficult to study everything around you using the computer which you have now, which is called a classical computer. You have a supercomputer. So in 1984, okay, Feynman formally gave the idea of the quantum computing, okay, what we are discussing nowadays. So he said, if you would like to study the nature, he gave the, okay, just simply conceptual idea that if you would like to study the nature, okay, then develop a quantum computer. The reason is, okay, everything around you in nature, okay, its working principle is not classical, its working principle is quantum mechanics. Okay, yes, for big objects like for car, for plane, for everything, big objects which around you, you can deal with them using classical mechanics. But if you are dealing with a small object like molecules, atoms, okay, different types of course atoms and molecules are very important for all type of chemical reactions, isn't it? Okay, you are a, a material scientist in physics, so you are dealing with the small particles. You are a high energy physicist, you are dealing with atoms, okay, particle inside the nucleus. So you can explain all these things by quantum mechanics. So he proposed the idea, but whenever, okay, so in a conference he proposed this idea, but at the end of the talk he said, I think it is difficult to develop a quantum computer. Okay, he was saying if you want to simulate the nature, if you would like to study the small anything in a nature, then you need the quantum mechanics. Every chemical reactions, every biological reactions happening in your body, you need a quantum mechanics to explain it. Now the second part of my question was why there is a too much delay. So first is no one has this concept, okay, of quantum computer. Okay, so the first time he proposed this particular idea. Major delay for the quantum computing is, as I was trying to explain you, quantum mechanics mainly to study the naturally existing quantum system. Okay, so you don't have any way by which you can develop your own quantum system. Can you develop your own molecule? Generally not, isn't it? You think about it, but generally molecules or whatever the structure you are creating, just like as you can make a table of any shape, you can make a chair of any shape, you can make a car of any shape, isn't it? So can you design the different structure of the molecules? Okay, generally not. Okay, because the chemistry of those particular molecules is very complicated. Okay, you think about it, you have some idea about it, you can generate it, but exactly, okay, it is very difficult. Yes. No, let's for example, we can do it, but it is not like a table. Let me give you an example of, in case of a uh, these diodes, you have nowadays flat screen televisions or not. Okay, so market is flooded with the flat screen, so they are LEDs or not, light emitting diodes. So you know how old is the light emitting diodes? Somewhere early 60s light emitting diodes were available in the market. So if you talk to the semiconducting physicist guy, they thought at the end of 1960s or early 1970s you will have these flat screen television sets. But it took us how much? Almost 40 years to have the LEDs. The reason was the blue laser was not available. Blue LED was not available. So that's what I'm talking about. So just if I want to tune up the band gap, okay, I said if this is the structure of my atom or molecule, I will achieve this thing. Okay, so you are right, we can synthesize it, but okay, if I give you a structure, can you, okay, for example, you can make the benzene ring, isn't it? If I say, can you make this structure? If I ask you, can you make this structure? Definitely you cannot. You got the point or not? So we can, of course, quantum mechanical systems, we can manipulate it, but they are not completely in your control. Okay, so generally you, in chemistry also, first you try the experiment. Once you have the experiment, then you try to say, oh, this is happening over there, isn't it? So it is not like a table or chair or something like this. You can make it in any design, but not in this one. So the major delay in a quantum computing is because you cannot develop, okay, your on demand quantum mechanical systems. Okay, even now for quantum computing, most of the platforms, okay, which you are using, they are naturally available. Okay, so artificially you are not creating the quantum systems. So the main delay is just like as, okay, you can make a semiconductor device of any shape or not. You can make a transistor, you can make a diode, you can make an IC, you can make it in any shape. Okay, so there is a lot of flexibility over there. This freedom you don't have, okay, in quantum systems. Okay, so the major delay in the technology is first, okay, we spend, and why there is a lot of delay to understand these things, that I will, that's my major focus of my talk is. Okay, I will not go to the details of mathematics, I will talk about it conceptually. So first thing is now before I move forward, still quantum mechanics is the theory in the history of the physics which is the most controversial theory, but it is the most accepted theory as well. Okay, let me tell you, if you want to understand, okay, the science of the laser, if you want to understand the science of the semiconductor, you can explain it only by quantum mechanics. Just like as semiconductor, yes, one more point over here is, okay, the band gap. You have the conduction band and the valence band. So this structure, okay, you cannot explain it by classical mechanics. So this was also a big question, okay, and start of the 20th century. Okay, so though you observe some semiconductors, and this question was at the peak somewhere in 1930s, 40s, and 50s, and there is no classical mechanics which can explain it to you, and you can understand how important theory of the semiconductors is. Okay, every type of communication around you is because of understanding of this. So you explain all these things using the quantum mechanics. Okay, so these are the some quantum mechanical system. So it took years and years, okay, to understand it. Once they finished the understanding of these things, they tried to reproduce it. Can you reproduce this structure on demand? Of course, impossible, isn't it? You cannot create an atom. You cannot create an atom. Okay, so in periodic table, you have 120 or 30, whatever the latest number of elements. Okay, you can discover the elements, but you cannot create a new element. Yeah, that's what I'm saying, in extreme condition. But if you ask them, okay, what are the structure you are creating, what is the life of that, they 10 is power minus 20 seconds, 10 is power minus 15 seconds. This is the typical lifetime of the particles, okay, which high energy physicists are creating. Okay, so of course, yeah, but we're talking about the stable structures. Okay, yeah. So now let's move on to this one. Now I would like to focus on, okay, what was the difficulty in these systems. So these systems, you understand it, but my talk of my focus of my today's talk is the platform which we are using for quantum computing. Okay, and what was new over there. So remember one thing, quantum computing is a buzzword, okay, and you use everywhere. So most important terminology should be quantum information processing. Okay, so it's just the information you are processing it. That information processing can be for your camera, can be for a sensor, and it can be in a microprocessor, isn't it? Microprocessor is doing what? It is just simply processing the information. Okay, so with this technology, what we are going to talk about today is, this is not only for quantum computing, it is for quantum sensing, it is for quantum internet, it is for quantum communication, it is for everything. Okay, so we are thinking maybe in next 20 to 30 years, maybe in 50 years, it may replace all kind of semiconductor devices which you have around you. Okay, so every sensor can be replaced by the quantum technology. You can have the quantum communication, you can have the quantum cryptography, you heard about it. So all these things can be replaced by the quantum computing. So so outcome of this quantum technology can be communication, sensing, simulation. So you can use it for cyber security, okay, for drug development, okay, for financial modeling, for batteries, clean fertilizers. So you can see it's everywhere. Okay,
classical on steroids.
Sorry.
Classical in steroids.
Yes, exactly. Yeah.
I mean, how classical doing more.
Yeah. So you can use it everywhere. Okay, as I said, okay, all the technology which you have, okay, they can be replaced, okay, by the quantum technology. Okay, when, how much time it will take, every, okay, for every application there are some hurdles we have to cross. Okay, so as I said, so quantum computing has an extraordinary this computational capability, and we'll talk about it, why they have. You can use it in a sensing technology and communication. I already had talked about it. So you can study the different chemical reactions. So it's everything. Okay, many things which you cannot do it by classical computer, you can do it on a quantum computer. Those who are working in a simulation area, okay, simulation of something, particularly if you are simulating atom or molecule, I'm talking about very small structures. I'm not talking about the simulation of the big structures. Okay, for example, if you have a 5 6 atoms and you would like to simulate it on a classical computer, you cannot do it, because the time you need on a classical computer without any approximation, okay, you need, okay, tens of years to simulate it, but quantum computer can do this simulation, okay, very easily. A supercomputer is also, if you remember in 2019 when the Google claimed a quantum computer with 53 qubits, okay, so their claim was if you connect all the supercomputers and you do the parallel processing, okay, it will take thousands of years, which their quantum computer was able to finish it in few hundred minutes. Thousands of years and few hundred minutes. Okay, so that's a basically in quantum technology, I say, as at the start I said, and during the lecture, at the end of the lecture, you will feel. So it is not an advanced classical computer. Quantum computing is not an advanced classical computer. Okay, it's just like as you may ride, okay, an horse in a very good way, but it doesn't mean you can drive a car. It's a completely different technology. Okay? Just like as you can be a very good driver of a car, okay, you cannot be a pilot. You cannot take a risk, okay, because you don't know any of the parameters, okay, how the plane, okay, is flying. It's a completely different science. That is something you need it over here also. So quantum computing is, okay, you have to learn few things from the scratch. Just like as, okay, if I cannot read the Arabic script, so no matter how much knowledge I have, okay, I cannot read a single sentence of Arabic. So I have to learn some fundamentals. I have to learn the Arabic alphabets. Okay, then I am able to read it, no matter how simple word you write it over here. If I don't know what is abatasa, so I cannot read it. So exactly the same thing with the quantum computing. This is a completely from the scratch. Okay, you have to learn few things for this particular technology. Okay, so as I mentioned, okay, your laser and semiconductors are the first generation of the quantum technology or the quantum mechanics. So the question is, if you explain this thing by quantum mechanics, you explain every atom, every molecule by quantum mechanics. So why I cannot develop a quantum computer with this one, or okay, with these systems? They are quantum mechanical systems, isn't it? So only the problem is in all these devices, whether it's a laser, it's a semiconductor, okay, or atom or a molecule. So you are studying their quantum mechanical properties, but your measurements are classical. System is quantum mechanical, but measurements are classical. Mean you measure the, okay, average of ensembles. Okay, so for example, okay, you are, maybe some of you are doing with NMR and chemistry, spectroscopy, okay, atomic spectroscopy, molecular spectroscopy, nuclear magnetic resonance, okay, emission spectra of the material. So you are doing this thing, okay, what kind of photons the material is emitting, but you are not measuring the individual photons. Okay, so over there measurements are classical, systems are quantum mechanical, but measurements are classical. For a quantum computing, I need a quantum mechanical measurements. Okay, and we didn't have the technology, okay, up to 1980s where we can do quantum measurements of the individual systems. Although from 1950s we are doing quantum measurements of the quantum systems, spectroscopy, lot of things we are doing it, but of an ensemble. So this is the second generation of the quantum computing, where you are using quantum mechanical systems and your measurements are quantum mechanical. Okay, your control is quantum mechanical. Yeah, this is the second revolution of the quantum mechanics. Okay, so now before I move forward, how different, as I said, is classical and the quantum computing? So the question is almost the same. Physically, I'm talking about one particular technology. This is the superconducting technology, and this is your classical quantum processors. You have other platforms as well, ion trap and other things, but I'm talking about over here in this picture. So it's almost the same, completely new science and technology. Okay, same with additional feature, okay, or it is just a fast classical computer. This is generally the question arises in mind. Okay, as you said, if you can do something with the supercomputer, supercomputer is replaced by quantum computer, small machine. No. So quantum computer is completely new science and new technology. Okay, so what is new science and what is new technology? That is something the focus of the today's talk. Okay, what is new science? Okay, and what is, so it's physically it's completely different, but this physical difference is not important for me. Okay, the working principle of this machine is very different from that one. Technology over here is quite different from that one. So what do you mean by completely new? So this is the typical model you use when you are dealing with the quantum processor. So you can see for every quantum computer, so now your classical computer, okay, yes, so you have for there, okay, right, okay. So every data, now see, and for a classical computer, you can give the data. How many ways you can give the data to the classical computer? What are the ways you can give the information to a classical computer? Ones and zeros from your side. Yes, image, text. You are going to the complicated, simple one, microphone, camera, isn't it? Keyboard, mouse. Okay, as you said. So there is a lot of ways you can give the data to your classical computer. In a mobile phone, you have many different types of sensors or not. So that's basically the data inputs, isn't it? But in a quantum computer, all the data will come from the classical computer. So once the quantum computer is available, so you cannot throw the classical computer. Okay, it is a very important part. So the data will come, okay, from the classical computer, and that data will be exactly the zeros and one. Yes. Yes, you have to use the classical computer. Okay, and we don't foresee at least next 50 years. Okay, we can get we can remove the classical computer completely. Okay, so there is no one is thinking about, okay, how to communicate directly with the quantum processor. Okay, as of today, for example, we are not thinking about how to connect a microphone to a quantum computer, how to connect a keyboard to it, how to connect a mouse to it, okay, how to connect any kind of sensors to it. Nowadays classical computer is connected to anything, isn't it? So you just simply use a proper modular device and you can connect it directly, but in quantum computer this is not the case. So the classical data and data would like to process, you will send it to a quantum processor, okay, and then you will process the information just like as a normal processor. Data will come from memory to RAM, okay, and then there is a quantum classical processor, you process the data and you just simply save the data or you read it, whatever it is. So data will be a quantum processor, and then as soon as you read the data, it become a classical data. So important thing somewhere here is, before you process the information, it's a classical data. Okay, you are done. As soon as you are done, your data will become a classical data. So before quantum processor, it's a classical data. Right after the quantum processor, it is a classical data. Why I cannot have a quantum data over here? Anyone? Why I cannot send a quantum data to this computer? That's because the data, okay, we'll talk about it. I will end that particular lecture. I'm saying, just for example, so from the keyboard, when you process you process different type of keys over there, 2 times 3, whatever it is. So these information are going to your classical computer or not? You press the 2, so it is generated a binary, okay, and then you say multiply by. So for multiplication, there is a command going to your processor, and then you say 3, then the your classical computer will process the information. So all these informations are traveling somewhere or not? All these informations are traveling in a certain, okay, certain electrical circuits. So that is your classical data. Quantum data is not like a classical data. So now that's a very important point. Now data over here is readable, data over here is readable, data over here is not readable, cannot be. Quantum mechanics don't allow you to see the data. As soon as you read the quantum data, okay, you know the quantum state will collapse as soon as, and it becomes a classical data. Okay, so you will process the information over here, and I'm saying you're processing the information, but you're not allowed to see. Okay, as soon as you try to see the data, okay, because when the data is going to the classical computer, this is the readable data, so it will collapse into a classical data. So this is the part, okay, we'll talk about what kind of this data is and how you will process it. Okay, quantum computer receive or deliver data, okay, to a classical computer. Nowadays there is no other options, you can communicate it. So in a quantum computer, the data will be in a quantum state, data will be in a quantum state somewhere here, okay, but as soon as you try to read the data, okay, the data will collapse. So the quantum data you are not allowed to read, you are not allowed to see. For example, if you have a if you have a problem in this quantum processor at this particular stage, in a classical computer on the motherboard, okay, isn't it, in the circuit board, if you have a problem, what you do, you take a meter and you check every device or not. Quantum computer you cannot do it. Okay, only thing is when you are getting something wrong over here, you have to guess where there is a problem. Today, tomorrow, after 100 years, as of knowledge of the quantum mechanics, you are not allowed to see, take a meter and check, oh, the data is in this particular form or not. So just like as whenever you have a circuit, you say, oh, voltage over it should be 2 volt, current over somewhere will be 1 milliampere, over it would be 0.7 milliampere, and so and so. This is something you are not allowed to do in a quantum computer. So this is the basic idea of a quantum computer. No, that is something I say science is new. I'm saying for quantum computing you need a new science and new technology. Just like I said, I know my mother tongue, I know the English, I can read, but Arabic script I have to start from the alphabets. There is no other option, because this is, I cannot say this A is similar to this, I cannot say the B is similar to this Arabic alphabet, they are completely different. Okay, to read that script I have to learn something new.
You said your science, you need a new quantum mechanics?
Yeah, no, of course all these guys don't know, electrical engineer don't know what the quantum mechanics is. Of course, mechanical COE guys, okay, you may be the very expert in making a programmer, you're excellent programmer, excellent compiler expert, AI expert, okay, you cannot work in this area. You have to learn certain rules, certain tools over here. Yeah, based upon your knowledge in a classical computers, okay, will help you over here, okay, but you have to learn certain new things. So now the question is, so whenever the data comes, so how the quantum computer work, whenever the data comes, you will convert this classical data, which is definitely combination of the zeros and one or not, you will convert this data at the first layer into the quantum data. Okay, at the first layer you will convert into a quantum data. I want to give you some idea over here, but I will focus on it. What do you mean by a quantum data? So now your input can be all zeros or not. So this is your classical data. Okay, I have the 4-bit processor, so 0 0 0, it can be 0 1 1. How many possibilities over here are? How many combination of these zeros? 16, isn't it? So for example, I am considering all these are 0 0 zeros. Okay, now I will use these circuits, these are the quantum circuits. For you there are just simply some blocks. So this is one of the quantum circuits. So in every quantum processor, okay, so these boxes are called gates. Okay, this is a CZZ gate, control Z gate, this is the Hadamard gate. Those who are working in this area, they know, have these X gate, Y gate, Z gate, Hadamard gate, just like as we have NOR gate, AND gate, NOR gate, isn't it exactly similar to that one? We are using this gate terminology. So in every quantum processor, the first layer of gate is the Hadamard gate. What the Hadamard gate is doing for you, it is converting that data, okay, into the quantum data. Okay. So now in quantum we use a special notation, not very different. So this particular state is 0 0 0 0 or not. So in quantum mechanics we put this, okay. So initial state is 0 0 0. So in a language of quantum mechanics we write this 0 0 0 state like this, just we put this special kind of bracket over here. So this is called the ket. Ket is just simply no name of a bracket. So this bracket is called the ket. So yes, ket and bra, two different notations. So 0 0 0, classically you write the data like this or not, 4 bits, this is the way you write it. Quantum mechanically you will write it like this. So your initial state will be represented by psi, okay. So so my initial state is this one, okay. So we use this ket notation. So my initials, I'm just simply giving a name to this state as psi. So after Hadamard gate, okay, so for you don't worry about it. So how is doing it, what it is, not important. What it is giving you, the state is this one. So how many possibilities over here? You said 16 possibilities over there or not? After Hadamard gate, you have how many possibilities? All 16 possibilities. See over here, 0 0 0 0 1 1 0 and so up to 1 1. So your classical data, some of you ask, what do you mean by a quantum data? So this is your classical data, and after this first Hadamard gate, this is your quantum mechanics. So your data is now, after first layer, it is present in this form. Now I will talk about it. What's the meaning of this? Okay, just you have to understand the meaning of this. Okay, and that's all. This is completely different for you, completely new for you. You understand what this data is, no matter, okay, what type of notations I put it over here. Okay, but this is your quantum data or the quantum information. Okay. So I would like to talk about it, what this data is. So this is the basic idea. Now as some of you said, this is the quantum. If I read it, okay, can I read this state? So whenever I'm going to read this state will collapse to any one of them. If I'm trying to read this state, how many outcomes are there in this state? How many possible states are there? 16, isn't it? If I try to read it, okay, I will read either this one or this one. Okay, so that is the purpose of the today's talk. What do you mean by this quantum state? Okay, I will develop, okay, the intuitive, okay, the idea behind it. What do you mean by this quantum state? So 16 states with equal probability. Why equal probability? What do you mean by this? I will talk about it, don't worry. So this is something I will go over it. Already I talk about it. Nature is quantum mechanical, but you cannot observe it. Quantum mechanics, yes please. Okay, just a minute. 200 mean, because this is the binary data always. So 0 and 1 is possible.
I mean, yeah, if it's, for example, 1 0 0 0, would it be the same?
No, it will be different, because this gate, okay, when input is 0, output is different. When it is 1, output is different. Okay, so for Hadamard gate, 2 possibilities of input or not? Possibility of the input can be 0 or input can be 1. For 0 input and for 1 input, output will be different. Okay, why it is different? We'll talk about it. Okay. So nature is quantum mechanical, but nature don't allow you to see it. Yes, please.
So the states in the slide are just only for the 0 0 0 combination.
For 0 0 0 combination. Okay. So you can understand any kind of data you can send. Okay, so it will change accordingly. Okay, and then you process the information. Okay, and then output will be accordingly. Okay, so nature is quantum mechanical, but it doesn't allow you to observe it. Okay, you have to believe in this thing, just like it's in a hydrogen atom. Okay, you have one electron or not? Electron can be in this state, can be in this state, can be in this state. Okay, quantum mechanics says that, okay, in this particular quantum, electron can be here, can be here, can be here, okay, at the same time. But just when you measure it, you will measure it in this state, or in this state. Okay, so in this particular state, for example, if I say this is my state 1, this is my state 2, this is my state 3. So the quantum mechanical state of this electron, I have only one electron in a hydrogen atom. So in a language of quantum mechanics, the state of the electron in a hydrogen atom will be, let's say, A1 B2 plus C3. That's the way the quantum mechanics, okay, explain it. This is the state of the electron in a hydrogen atom. But one electron can be at 3 different places? Of course not. One electron will be at one place. But quantum mechanics says that this electron can be at 3 different places at the same time. The probabilities, but there is a slight difference between the probability, okay, or whether it is present at 3 different places or not. Let me give you an example. Now I will talk about the superposition a little bit more detail. Just give me 5 minutes. I will be back to your this question. What do you mean by this state? How you exploit it? I understand in what language you are talking about, because you are a chemist and you know you are using this particular, okay, in terms of probability and so and so. But now I would like to use these states. I would like to talk about these states in language of quantum computing. Okay, I don't want to talk about it a chemical reaction. I would like to talk about it, okay, in a language of quantum computing. Anyway, cannot be observed, cannot be measured. This is the postulate of a quantum mechanics. Upon measurement, the state will collapse, okay, into a specific state. Let's see, what do you mean by this? What is the working principle of quantum mechanics? For example, generally, okay, at this time I am at home. Generally I stay at home at 7 o'clock, but today I am here. Okay, so the quantum mechanics says that, okay, I can be at 2 different positions at the same time. I can be at 2 different positions at the same time. For example, I can be at home, okay, and I can be a okay, in this lecture hall. So there is certain probability, yes, it makes sense. So generally I am at home. So someone will say 90% I am at home, 10% somewhere else. This is my quantum state today. Yes, but you say, yeah, it's normal. I can be at home, I can be in the lecture hall. Most probably at home, but there's some chances I can go for shopping, I can go somewhere outside, and so and so. So, so my quantum state over here is, so instead of, let's for example, I write it 90% at home and 10%, okay, in this lecture hall. This is my quantum state. Make sense or not? Okay, now can I measure this state? So no, this state I cannot measure it. Okay, so when I measure it, for example, you want to make sure where I am. Okay, so what you will do? You will give a telephone call or not? And I will say, I am at home. So depending upon, if you repeat this process, 90% chances are there, 10% chances are here. So for example, someone is saying, okay, I am in a quantum state, I am at home as well as in lecture hall. So you will ask me, can you show me that I am 2 places? Quantum mechanics is claiming what? I am at 2 places at the same time. But if you try to measure me, you will measure me either in home or either here. So classically same, quantum mechanically is also. But what's new? Nothing new. But important thing over here is, when I measure it, either I will measure it at home or in lecture hall. But interesting thing is, if you assign me 2 jobs, one at home, one here, you can see the work done by me at the 2 places at the same time.
So what is the meaning of the probability?
Yes, yes. It makes sense or not? This makes sense classically. 90% chances at home, 10% over here. It's perfectly all right sentence, isn't it? Okay. If you measure it, either I will be at home, I will be in the lecture hall. Perfectly all right. If you measure it, I will be at one of the two places. That's quantum mechanics is saying. Classical mechanics is also saying the same thing, isn't it? But quantum mechanics says that you are not allowed to measure where I am. This state you cannot measure it. If you measure it, my state will collapse, either home or hall. You say you are using just a different kind of language, but it is same as, okay, we use the terminology in everyday life. But what the quantum mechanics is saying, if you assign me, give a lecture in the lecture hall and at the same time watch movie at home, so you will see that I am doing both the jobs. For example, I am writing, okay, a paper over here and I am just simply teaching someone at home to my kids. So you will see my output at both the places. You cannot, yes, you cannot measure me, but you can measure my jobs at two places at the same time. So this is something you need it if you are working in this area. Communication, sensing, computing, network, internet, anything. This is something you have to just simply change your your intuitive ideas. You're getting my point or not? So I will focus on this particular point again and again. Okay, anyway. So as soon as you measure it, the state will collapse. But if you assign, I can be at three different places at the same time. Quantum mechanics says that this electron is at three different places at the same time or not? I can be at three different places at the same time. Okay, I can claim I can be at three different places. But you say, can you show me? Can you give a video call to him at three different places? I say, no, you cannot see him. You cannot make a video call. So quantum mechanics says, what's the proof? You will ask, what's the proof of quantum mechanics? If you assign me three jobs at three different places, you will see my jobs, work done by me at three different places. You cannot see me, but you can see work done by me. That is something in a quantum computer. You will use all these 16 states with one clock pulse. All these 16 states which I showed it to you, okay, so data will process, okay, all these 16 states you can process with one clock pulse. Classically, if you have a 16 combination, how many combinations are there? 16. Okay, you can process one combination one time, isn't it? You need a second clock pulse, you need a third clock pulse. Okay, so but in quantum computing, you can do it, okay, all at the same time. But don't worry. Now I'm going to talk about from where these ideas are coming. You are moving, and in front of you there are two doors. Which door you will cross? Either one or two, isn't it? Can you cross both the doors at the same time? No way. But this is the quantum mechanics. You will cross both the doors at the same time.
You are aware.
Thanks for the clarification. But the web can pass through.
No, no, just a minute. Just exactly this is the point I want to clarify. This is something you cannot explain it by quantum mechanics. Okay, that's what I'm saying. You are the single person. Okay, if you are a wave, I will talk about that wave concept also. Okay, so because the wave concept is not simple over here. Okay, so there is a one person and there is a two doors in front of him. So what the quantum mechanics says that you have to believe you are crossing these two doors at the same time. Mean you are going to split up, you make a carbon copy of yourself, but you are crossing both the doors at the same time. So the quantum mechanically, okay, you can cross both the doors at the same time. This is the working principle of the quantum computing. Okay, this is not just simply I'm trying to make some new theories. This is something you are using it nowadays. This is something you are using it. Okay. So, however, this step we cannot observe, we cannot measure. For example, you say let us put a camera over there, okay. So, camera will detect it only through one door. Okay, if you switch off the camera, you do not observe it, okay, you have to believe me, yes, I crosses both the doors. Okay, I will show you very interesting thing related to it, very interesting experimental observation. These are not the theories, these are the experimental observation. So, the quantum mechanics says that you can be at the two places at the same time, okay, and this is something I will show you the experiment. And by the way, this experiment we are developing at KFUPM also in upstairs. So, we are hoping by the end of the summer this experiment will be ready. You will be able to do this experiment with the photons. Yeah, it is because I placed the order of I started that establishing that lab in 2019. Then because of the COVID, the supply chain is disturbed, and you know, in the KFUPM purchasing part of the senior lab, I would like to introduce as a part of the senior lab. So I want you to feel it. I hope inshallah it will be ready. Anyway, let's see. So this is something Young's double slit experiment, you know very well. The wave passes through the two slits, okay, and you explain this crust and trough, isn't it? I hope all of you can recall it. With wave theory, you can explain this particular interference pattern, okay, very successfully. So how you explain it very quickly, I will go over it. So there are two slits, S1 and S2. So now at this particular point, so these waves are in phase. So two wave trains are traveling same distance, okay, with the same speed. They will reach at the same time over here or not? So from one source you will have this wave, from other source you will have this wave, and when these waves are going to overlap, their amplitude will become double or not? That is how you explain it, interference pattern. Now if you are somewhere here, this wave is traveling less distance, this wave is traveling more distance, okay, if this difference is lambda by 2, so at this particular point from one source you will get the wave like this, and from other one you will get the wave like this. There is a delay or not? This train will reach late. So over here interference is destructive. That is how you explain the interference pattern. If you repeat the same experiment with the electrons, you will see this wave pattern. That is a wave particle duality. So instead of a light, if you use the electron beam, okay, then you will see the same wave pattern. That is something your friend was saying, wave particle duality. Every particle can act as a wave, every wave can act as a particle, okay. So this is based upon the wave particle duality. So you explain this experiment very successfully with the help of wave nature. Now I would like to jump on this experiment. Now if you send the photons one by one, will you see this interference pattern? So I am sending the one photon and I will wait, and you know the photon will take how much time to go. So there is a source of light. This light is split into two parts, isn't it? Light is generally coming from the one source, and then it is going to split into two parts. Now I have the light source over here, but I make sure the source is producing one photon at a time, okay. Release the one photon, then wait, release the second photon, then wait, release the third photon, and then wait. One of the physicists completed this experiment in how much time? 6 months. He wanted to make sure that time interval between the two photons is large enough, and he was able to see the interference pattern. We will talk about it. Then you have to go to the quantum optics, quantum electrodynamics. I have to go to the advanced level physics, but this is something which is possible. A total, all spectrum. Or for example, you have a doubt about the electron, you send the electrons. Is it okay? If you are not comfortable with the photons, electron, you have the good control or not? Chemistry, you have the good control over the electrons. So you are sending one electron and then you wait. You want to wait 1 minute, 5 minutes, 10 minutes, it's up to you. So send one photon on one electron, and enough time difference in between them. Okay, you know the light is traveling at a speed of 3 into 10 8 meters per second. So you are giving an interval of 1 minute. It's very large, isn't it? That photon for sure it is over here absorbed by the material or it is settled down. If you complete this experiment, okay, with one by one photon, you will see the interference pattern. How to explain it? The question is how to explain it. Yes, interfere with itself. So you are using this term exactly, it is going to interfere with itself. So this is possible if it is going through both the doors at the same time. That's what he is saying. That's the only way to explain it. It interferes with itself. So if you use this terminology, so it's mean this electron or this photon which is coming alone is passing through these two doors at the same time. Yes, sending two electrons. Okay, sending two photons or more than two photons. Okay, it is going to split up. I will talk about more experiments as well. This is the only theory. Exactly, that's a very good point. As I said at the start, quantum mechanics is the most controversial theory. Some say that this is all foolish, but we don't have any other theory to explain it. That's exactly the point is. Why it is most controversial? People saying Einstein spent 10 years of his life, okay, to improve this. He didn't believe in this thing. Particularly, he don't have the issue with this one, he has the issue with entanglement. I will talk about it. He said entanglement is something a foolish idea. Okay, he was very desperate in last 10 years to disprove the theory of the entanglement in quantum mechanics. But as of today, we don't have any theory to explain it. If we don't have the theory, what's the option? We have to accept it. So in reference to your question, physicists are interested in the quantum computing not to do the computing. They want to explain the quantum mechanics in a better way. So all physicists, they spend less time on the computing side. That's why in last 20 years there is less development towards the computing side. Okay, because whenever there is some development, they go towards the physics side. Okay, so they're more interested in a physics side. Okay, so they're thinking about this theory is not complete. Okay, let's improve it. If you have the quantum system, they think they can improve it. Okay. So now if you have send the photons one by one, what type of pattern you will see on the screen? You will see exactly the same interference pattern. So the question is how to explain it. Now, now the question is, so scientists were clever enough, so if you're sending the photons one by one, you see the interference pattern. Okay, but it's a multiple waves. It's a collective property exactly. It's a multiple waves can generate this interference pattern. If only one wave is coming from somewhere here, so either wave will cross this one or wave will cross this one. But the quantum mechanics is saying it passes through both of them at the same time. Very interesting thing is, now for example, you have the interference pattern, you're sending the particles one by one. Now you are clever enough. You say, I want to see whether it is crossing this one or this one. You can put a microscope over here or not. As soon as you put the microscope over here, this pattern is gone. As soon as you measure it, I'm telling you it passes through both of them. Now if you put a microscope over here, you put any kind of detector, electron is a charged particle or not? So when it crosses this one, there will be some charge detector, you can put it over here or not? As soon as you put the charge detector over here, this pattern is gone. Yeah, it's because as soon as you measure the quantum state will collapse. Or for example, you put a source over here in such a way that you know the first particle will pass through this one, second will pass through this one, third will pass through this one, okay, fourth will pass through this one, interference pattern you will not see. If you have any information directly or indirectly, okay, quantum state will collapse. Okay?
Will you go either one of them?
as soon as you try to see, the interference pattern will be gone. Yeah, this is, that's exactly I'm saying there's a big question mark. Okay, so quantum theory explained it successfully. Now I will go to few more. That's what I'm saying over here. As soon as you put the microscope and you would like to see the electron or the photon passes through which of the slits, interference pattern is gone. Okay, as soon as you measure, the quantum state will collapse. Now let's see a few more experiments, really interesting experiments. So quantum mechanically, the state, I introduce some notation, then I will go to some theories and I will go back and forth. So ultimately I would like to talk about a language of 0 and 1. If you have a single two quantum bits or two transistors, so their states can be 0 and 1. Okay, one qubit can be in a 0 and 1, one transistor can be in 0 1, one switch can be 0 and 1. Two bits, what are the possible states? 0 0 0 1, 1 0 and 4 1 1. So these four states can be possible, okay, in a quantum system. If you have a 3 bits, so possible states are 8. 4 you have 16 qubits, 16 possible states, and so on. So your system can be in all these states. If you have two switches, just like as two switches, okay, both of them can be on, both of them can be off, on, off, off, on, isn't it? But quantum mechanically they can be in 4 different states at the same time. 4 different, yeah, 2 to the power n, exactly. So they can be in 8 states, 4 states at the same time. Okay, but you are not allowed to measure it, but they are controlling the lights or not. So you can use the or fold combination of these lights at the same time. Both lights can be off, both can be on, one is off, other is off. 4 different states or not. So you cannot see it, you cannot measure it, but with these lights, if you are doing something, you can do all 4 states, you can use all 4 states at the same time.
Do they exist now?
Yeah, that's what you are doing in a quantum computer.
So if you connect it to a light,
Yes, if you want to process the 4 states at the same time, you will process it.
if I'm outside the room, will be in that state. If I enter the room,
Yeah, it will collapse. Exactly, this is the working principle of the quantum mechanics. Okay, now let's see. So quantum mechanically they can be in a 4 states, 8 states, and so at the same time. Let's look at it, another interesting experiment. I hope all of you are familiar with the polarizers. Okay, so this is unpolarized light. When it passes through a vertical polarizer, so only vertically polarized light will cross. Okay, and if you put a horizontal polarizer in front of it, there is no light behind it, isn't it? So in the first case, the first polarizer is vertical one, second polarizer is horizontal. So what's the light after the second polarizer? No light, nothing. Now if you rotate the second polarizer, just like as over here, if you rotate the second polarizer over here, you will get some light over here. This is something you can explain it by classical mechanics, isn't it? Nothing new over here. This is purely a classical mechanics. Now this is the vertical polarizer, horizontal polarizer, no light or not? Now over here you can explain it. Vertical polarizer, horizontal polarizer, but if you put a polarizer at a certain angle, okay, you will get the light after it. Okay, makes sense. Now the question is, if I'm sending the photon one by one, will I get something over here? I'm sending one photon. This photon is either vertical, horizontal, or something like this, isn't it? So this one only vertical photon will cross, isn't it? I'm sending one by one. I make sure I'm sending the one photon, wait, send the second photon and wait, send the photon and wait. So when you are sending the photons over here, whatever be the time delay in between, only vertical photons will cross somewhere here or not? Okay. So if I am sending the one by one, okay, one photon, then second photon, third photon, so what is the probability of getting the photon over here? Okay, so theory is telling me the photon somewhere here is vertical and this photon cannot cross this one, isn't it? Yes, this is the case over here. Photons are vertical. Over here there is no photon. I do this experiment with 100 photons, with 1000 photons, with million photons, I will not get a photon over here. But if I do the experiment over here, I put another polarizer over here, I am sending the photons one by one, I will get the photon over here. How to explain it? Something, I will talk about it, how many I will get the answer, but the question is, I will get the photons over here. How come?
What do you mean by vertical photon? I mean, it goes in a vertical way.
Yeah, because the light is electromagnetic waves or not? Light is electromagnetic wave or not? So electromagnetic wave, light means there is electric field. Electric field is a vector quantity. So the electric field of your light is vertical because it's a vertically polarized photon. If the light is horizontally in a horizontal direction, we say it's a horizontal photon, because the light has two theories, okay, wave theory as well as the particle theory. Okay, so polarization is related to the wave theory. Clear this point? So the light is always electromagnetic waves, either you consider the electric field or the magnetic field, both of them are the vector quantities. Okay, so they must be in a certain direction. Okay, so I allow only vertical electric field to cross. So how? Okay, some of the horizontal field can cross through this one, because it has no horizontal field, it's only vertical field. In a vertical vector, is there any way you can get the horizontal component? No way. Simple. If you have the, because I, j, k are orthogonal to each other or not? I cannot be expressed in terms of j and k. These three vectors cannot be expressed in terms of one another. Every vector in the universe can be expressed in terms of I, j, k or not, but I, j, k cannot be expressed in terms of one another. Okay, so over here I cannot explain. I do this experiment and I am getting the photons over here. How to explain it? Okay, there is no way to explain it except this controversial theory of quantum mechanics, counterintuitive ideas. Okay, now in this case, if you rotate this polarizer, you will see very interesting thing. When the phi is 0, mean this is also a vertical polarizer, okay, or I put this polarizer at an angle of 45 degrees and at this polarizer at an angle of 90 degrees. Okay, I am sending the photons one by one. I am observing, doing the quantum mechanical experiment, not the classical electromagnetic waves. I am sending the photons one by one. If you put this polarizer, middle polarizer, okay, at different angles, you will see, okay, there is a light at 0 degrees, 90 degrees no light, 45 degrees there is a light, and the probability of getting the photon is very interesting, 50%, 0% and 25%. If you send the 100 photons, 25 you will get it over here, okay, in this case. In this case 50% will cross this one. If you send the 1000 photons, 25%, 250 you will get it over here. If you do this experiment, there is no way you can explain it using classical mechanics. Why I am talking about all these? Because these are the all quantum hardwares. These are basically all quantum hardware platforms, and you are using these things to develop a quantum computer. So these are the quantum hardwares. Okay, I am spending time on it, so I am just simply indirectly explaining you, okay, what kind of quantum hardwares are there. Now the question is how to explain this thing. So there is only one way. So the physicist said every photon which is, even you are sending one by one, you are sending the photon one by one, every photon from your source is in this state, 50% vertically polarized, 50% horizontally polarized. From where I wrote this equation, as we talk about it, this is the only way to explain it. You may come up with new equations, with new idea, with new concepts, but this is the, as of today, that is the only way to explain it. And it is why we are accepting it, because no contradiction. As soon as there is a contradiction, of course all this building of the quantum mechanics will collapse and you have to come up with the new theory. Okay, but as of today there is nothing. So now what the quantum mechanics is saying, so now vertical photons are crossing over here, okay. And after this one there is no light. So now what they are saying, what this polarizer is doing, this is the vertical photon or not? As some of you said, when you apply the Hadamard gate to 0, okay, or Hadamard gate to 1, isn't it? Some of you asked this question, okay, Hadamard gate. So some of you ask, okay, instead of 0, if this is 1, what will be the output? Yes, output over here and here is same, but over here will be different, okay. So that is something indirectly I am explaining it. So now they say when the light passes through this one, it creates again a superposition state. So what was your original state? This polarizer is creating this state again. How? We don't know. That's the only way to explain it, okay. So you can see the vertically this light is this quantum mechanics says that from the source the light is in this state. When it passes through the vertical, it blocks the horizontal, okay, horizontal is blocked, only vertical is crossing. Now if you crosses this one, now you can see both horizontal vertical are there or not. Now the horizontal can cross this one or not, okay. If you remove this one, nothing is there, but if you put it over there, because this is going to create this superposition state. So in a language of quantum gates, this is the Hadamard gate. This is just an Hadamard gate. So if you are working on an optical quantum computer, so this polarizer at an angle of 45 degrees is your Hadamard gate. Okay, so there was no way to explain it other than this theory. Yes.
Can we treat this polarizer as the same as the double slit, the two slit in the double slit experiment? Also split.
Yes. I will talk about that one also. That also is a part of my slides. Okay, now, so these are the few things over here. That's exactly, so in a language of quantum mechanics. So let's see, vertically polarized light. So detector will, probability will be 100% or not. Every photon is vertically polarized, will cross this one. So detecting probability is 100%. Over here, this is my quantum state. So what is the probability of getting the photon? 50% or not? Because the equal probability of the vertical and the horizontal. Yes. Yes, doesn't make any difference. All these equations are, I will talk about it. That's also very interesting. That's also very interesting. It's positive or negative. Okay, if I reverse their positions, so this sign will become negative. Okay, but I don't want to go towards that direction. So your question is, if I replace vertical with horizontal and then I'm going to reverse this process, then I will use the negative sign over there. Anyway, let's move on. So now I can create this state as well. It's not 50-50 always. It's not always 50-50. From the source I can generate these states also, but I don't want to go to that particular detail. There is another experiment in the physics. This is the one of the most important experiment. All these equations, okay, are the second phase. So all these states which I am writing it over here, the quantum states of this light, before, after, all these states, the scientists developed it, okay, with the spin of the electron. Okay, Stern-Gerlach experiment. Okay, so this was the experiment. It took scientists years to explain it. Okay, when this if you have an ion, okay, spin half particle, you pass it through a non-uniform magnetic field. So first they thought, if you have a vector, you can think about it, if there is a vector and you are measuring only the vertical component, okay, so you will measure this this vector. How much is the vertical component of this? 0. This one, certain percentage or not? 50%. This has 70%, 80%, 90%, and this is 100% vertical. Okay, so now physics is telling you from this O1, okay, particles are coming with the different spins, spin in all possible directions. But when they measure it, they thought, okay, they will measure a different component of the spin. When they measured it, they measured only 2 spins, either spin up or spin down. This is the theory. Okay, so particles have different spins, but as soon as you measure it, it will collapse into up spin or the down spin. So let me go to the block diagram. I don't want to teach you the theory behind it. Let's move on to this block diagram. So what this Stern-Gerlach experiment? So this is the source of the spin half particle. You apply a non-uniform magnetic field along the z direction. So originally we thought, okay, we will measure the spins, different component of the spins, when the particles are going to hit the screen everywhere. But when they did the experiment, okay, the particle are hitting at the top or at the bottom. So it means whenever you measure the spin of the particle, spin will collapse either up or down. So from the source, particles with no preferred direction of the spin. So if you measure the Stern-Gerlach, 50% will go up, 50% will go down. Now let's see. Now if this is my setup, this is the source producing the spin half particles. So I put the Stern-Gerlach over here. This setup is what? This block is representing what? There is a non-uniform magnetic field in z direction. Some particles are going up, some particles are going down. What percentage over here? 50% over there, 50% over here. Makes sense or not? Now I put another Stern-Gerlach z experimental setup over here. Okay. So what is the probability over here? Here is 50-50. What is the probability of getting this? What's the probability of getting this? Okay, now somewhere here, spin up and spin down. 50% spin up, 50% spin down. Over here I block the spin up, only I have a spin down. Okay, so now in this beam, do you have any spin up? No, so only spin down. Okay, so if you do this experiment, 50 and yes, 100 relative to this, you are right, relative to this 100%, but relative to this is 50%. Makes sense? Yeah, what are the reference you are using? Okay, so this is something you will observe. So that's something we say, if you do the quantum measurements and when you repeat it, you will measure exactly the same thing. I measured this measurement and this measurement is exactly same or not? So if you do one type of measurement in a quantum system, if you repeat those measurements, you will get exactly the same result. Now let's see this one. This is something I copied it, the last one. I have SGZ, SGX and then SGZ. Okay. So now over there 0% and 50%, isn't it? Now over here 0%, 50%. What you will get over here? There is classically, of course, there is no way to explain it. Okay, but when you do this experiment, for example, you are saying this is 50%, isn't it? This is 25-25. You block the spin up or not? What you will observe over here? This is 50, 25-25. What it will be? 0-25. But you will see 12.5, 12.5. This is just spin particles are coming. You have to apply the magnetic field along z axis, magnetic field along x axis, magnetic field along z axis. You can do this experiment very easily. So there is no way to explain it. You said I blocked the spin up particles, but you are getting the spin up particles again. How? From where you are getting it? It is exactly like I block the horizontal photons or not. When I put a polarizer at an angle of 45 degrees, horizontal was generated again or not? What I am saying over here, I block the horizontal or not? So they are appearing again over here or not? I block the horizontal over here. But when I put it in 45 degrees, so horizontal is generated again. From where? We don't know. That is the only way to explain this observation.
It doesn't matter if we increase the number of filters.
Doesn't make any difference.
So SGX considered as an Hadamard gate.
Yes, yes, exactly. So this is the Hadamard gate for this one. Okay, and this is the this is the Hadamard gate for this output. Okay, that these are the Hadamard gates. This is a very important type of gate. And for physicists, it's very obvious. See, at the start I said how to create a superposition state. I'm creating the superposition state or not? Now I'm going to use it mathematically. So now this is 0 and 50%. So I'm assuming over here there's some type over here. I'm writing this 50-50 relative to this one. This 50-50 is relative to this one. So now this is 25 and 25. If you look at it from this reference, it will be 12.5, 12.5. There is no way to explain it. I block the spin up over here, but I'm getting the spin up again over here. How to explain it? Because this is the physics. The physicist says that the z has these two components along z axis. Okay, so this is the state over here. That is the only thing, only way to explain it. So they are creating the superposition state or not? One in a superposition state, one in a superposition state. That's how you create the superposition states. That's how you create a superposition state. I will talk about it a little bit in more detail also. Let's look at it. You have a beam splitter. So this is a partially reflecting block, which is very normal or not? Whenever you have a window in the glass in the window, so some of the photons are reflected, some are transmitted or not. 100% transmission is not possible. So this is a semi-reflecting glass. So for example 50-50, okay, it's reflecting and 50% it is transmitting. So now if I do this experiment and send the photons one by one, so detector D1 and D2 clicks. So probability is what, 50-50 or not? I am sending the photons, sometimes it will reflect and sometimes it will transmit. So this block is made of a material. If I shine the light, okay, normal light, so 50% of the light is transmitted and 50% is reflected. If send the photons one by one, so both the detectors will detect and the probability is 50-50. So I can say this block is creating this state or not? This block is creating this state. Sometimes it is going up. If it is going up, I call it say state 1. If it is going in this direction, I say state 0. So probability is 50-50. I will go over it now a little bit fast. 50-50 beams, not a 50-50 beam splitter. So if it is not a 50-50 beam splitter, you can create any superposition state. But this is not important. Let's focus on that one. Now let's see the interesting thing. This is my 50-50 beam splitter. The photon is coming and sometimes this detector is clicking, sometimes this detector is clicking. So I am saying at the output, this is my quantum state. Let's look at it. I have two beam splitter. Transmit it, then I put a mirror over here, simple mirror, guaranteed reflection. I put a mirror here, guaranteed reflection. So when these two beams are going to combine, so if my input is 0, which of the detector will click? Both or one of them? I am sending the 0 photon, 100 photons, but one by one. One photon, second photon, third photon. So which of the detector will click? D1, D2 or both? I am not asking about the probability, I am talking about which of these two detectors will click. So originally what it is, just a minute before I move forward, when the 0 photon is coming, sometimes this detector is clicking and sometimes this detector is clicking. If sending 5000 photons over here, 2500 I will detect it over here, 2500 I will detect it over here. Clear this point? This is the property of this block. The property of this block is to split 50-50. Now I put the two blocks, okay, reflected, go in this direction, transmitted, go in this direction, and then again there is a block, it could be transmitted, it could be reflected. If I send this photon, so my question is, if my input is these photons, for example such kind of I am sending 1000 photons, this 0 can be vertically polarized photon or horizontally polarized photon, H, V or 0, 1 we can write it. So now if this is my input, which of the detector will click? I am sending 1000 photons similar to this one, but one by one. Okay. If you do this experiment, very interesting thing you will observe, only D1 will click. So only D2 will click, D1 will never click. That's a quantum mechanics we need. So these are the experiments, okay, we perform and we are not able to explain it. In this case, always you send this 0 photons over here, always this detector will click. This will never click. Now you can see somewhere here when this photon is coming, it may go in this direction, it may go in this direction or not. Over here it should be equal probability or not. When you do this experiment, always this one is clicking. That's exactly. There is no way to explain it. Because over here it may reflect, it may transmit. Over here, no matter coming in this direction or coming in this direction, it may transmit or it may reflect, isn't it? It has a reflection transmission probability, it has a reflection transmission probability. But the question is why, okay, whether the photon is coming from somewhere here or the photon is coming from somewhere here, both of them are going in this direction. Why none of the photon, this photon has equal probability to go in these two directions, this individually has equal probability, this has equal probability, but why only this photon is always going there?
I think if you assume that at each time you send a, for example, signal, the reflected wave will always be in state 1 and the transmit 1 will be always in state 0. So if you see a detector 1, it will combine both states together, so this should be 0.
So the question is how you explain how they combine them. That's exactly the question is.
Yeah,
okay.
Because at detector 1, it will detect both states from different directions. But at detector 2, you will have the same states, which are 1 at detector 2. So there's no way that you can get, you cannot detect at D1.
Okay, now let's talk about it mathematically. So what I'm saying, so when the 0 is coming, output is that state or not? Okay, and so quantum mechanics explain it how. When the input is 1, the output is this one. Okay, so now when this state is going to this one, output will be this one. When this state is going over there, output is this one, and they are going to combine over there or not? And if you solve this simple equation, you will get all this. So they are creating the superposition state. Okay, now I will spend not it's already 8:50. So there are a lot of similar experiments which you cannot explain by quantum mechanics, by classical mechanics. That's the only way to explain it. So all these things are creating the superposition state. Mean if the person is coming, there is a 2 doors, he is crossing both the doors at the same time. In all these experiments, this is the theory behind it or not? They are creating a superposition state. This block is creating a superposition state. If the photon is coming from Z, it passes through the X, it is creating a superposition state. That's the only way to explain these experiments, and we are accepting it. So similar experiment, let me go over it. So now the quantum mechanics is, quantum computer is completely different science. Okay, just like as I give you just this example. So when this filament lamp was invented, no one was ready to believe. So when they market this filament lamp, what they claim, they say its life is infinity or it will work for years. So before this lamp, what was the concept of a light? If you want to generate a light, you have to burn something. So they thought if they need a light for more time, then they have to burn the more material. When they look at this lamp, they say, oh, small piece of element over there, it will burn in maybe in 5 minutes. They thought the shopkeeper is cheating us. They are saying just take it and it will work for years. They thought this small element, no matter how slow you burn it, it will finish in 5 minutes. Okay, but they didn't knew it's a completely different science. It is not the advanced version of this one. Over here you are generating the light completely in a different way. That is exactly the quantum computing is. It is not the advanced version of a classical computer. It is a completely different science you are using. Okay, which is controversial. You have a lot of questions in your mind, but it is working. So the quantum states is, if you have a 10 qubits, the number of states are this. If you have a 50 qubits, number of states are this. Okay, so you can see in the 50 qubits you can have 10 to the power 15 states at the same time. Okay, now I would like to give you some idea about it. If you flip a coin about the quantum states, I would like to, maybe in 10 minutes I will finish it. If you flip a coin, if I ask you what is the state when the coin is in air, what is the state, head or tail?
50, not 50.
Yeah.
It depends on the.
So when the coin is in air, okay, classically it has no state, isn't it? But the quantum mechanics says that, okay, it has both the states, okay, head and tail. But why classical mechanics don't believe in it as a head or tail? For example, he and me are playing a game, okay, I flip the coin, if head comes, I won, okay, I am going to win the toss, okay. So still in air, I say it's head, okay, I win this toss, okay, will he agree? So classically it has to land.
We only believe by observation.
Yeah, of course. But why? The reason is, if it is in air, can you process any information with this coin? You can decide who is the loser and who is the winner? No. But quantum mechanically, if this coin is in air, you can use it. You can process the information. Okay? So quantum mechanically, it is in both the states at the same time. When it is going to land, okay, it is in a classical state, but you can use the states when it is in air. So if you flip the two coins, so possible states are, these are not classically also, these are the possible states, okay, but classically you cannot use it. Quantum mechanically you can use this state. The system is in in different states. Same thing with the dice, you can do it. Now let me summarize this one, not over here, yeah, out over here is fine. Okay, now if you throw this dice, what are the possible outcomes? 6 different outcomes or not, with equal probability. Okay, in quantum mechanics, let me give you an example over here. So remember, quantum mechanics is probabilistic, not deterministic. Let me give you a very simple example. If you give this command to a quantum computer, what is the possible answer? Classically what it will be? 15. But if you give this command to a quantum computer, so the quantum computer answer is sometimes 9, sometimes 12, sometimes 15, 0, 1, 3, all possible, 15. These are the possible outcomes. So what kind of useless computer it is, isn't it? Yes, this is the reality. Okay, whenever you give a command of 3 into 5, this computer will give you answer of 9, 12, 15, okay, 0, 1, 2, 3, and so on. So these are the possible answers. Of course, depending upon how many qubits are there. Okay, so generally I'm using a 3 qubit processor over there, or 4 qubits. So total combination is 15. Okay, so now these are the possible outcomes. The question is how to decide. Okay, so if you want to do this processing, so what you will do, I told you whatever will be the input data, this is the classical data or not, you will convert into a quantum mechanical data. And what is the quantum mechanical data? All possible outcomes with equal probability, isn't it? All possible outcomes will be equal probability. Then what you do over here, you write an algorithm. What the algorithm will do, will increase the probability of this 15 and decrease the probability of all others. But you write an algorithm in such a way, this probability is not 1 and probability of the rest of them is not 0. If it is 1, rest of them is 0, it will become a classical computer. Okay, so if you don't write any algorithm, your output will be, you plot the histogram over here. How many outputs over there? 15 outputs with equal probability. Okay, so you write an algorithm and you increase the probability of the required outcome and you decrease the probability of the unwanted outcome. So now if I want to do this multiplication, I have to run this loop how many times? Nowadays we run 4,000 times. I give a command to classical this quantum computer 3 into 15 and I give a loop to the classical computer, do it 4,000 times. Classical computer will collect the data and will give you the histogram.
Even if you have bigger numbers.
Even you have that. That's exactly the next point of it. So you will plot the histogram and then your classical computer will pick the maximum histogram is your output. It's useless. 3 into 5, you are running it 4,000 times, but think about it. If you have a trillions of data, you do the same thing 4,000 times. So the quantum computer is very useful for huge data, not good for small data. So it means there is no way you can replace your classical computers. But of course, if you have a trillions of data and you want to pull out something out of it, so you have to run it half a trillion times minimum or not. Different protocols you are using it, but a quantum computer is probabilistic. Okay, so it is basically in this dice. If I want some specific output 6, so what I will do? I will load it from somewhere or not. That is called the cheater's die. So algorithm is what? The loading it from one side. So you increase the probability of the output of someone. So your algorithm is making the probabilistic system little bit biased. Okay, so quantum computing is probabilistic, not deterministic. Okay, that's what I explained it to you. Okay, so you cannot, if you make it deterministic, you are gone. Let me just move on to the few more examples. You can read it yourself, that I already explained it to you. Let's look at it. There are 5 lamps are inside the this black box. If I ask you which of the lamp is on or off, of course you cannot answer it. If you remove it, this is the state or not? Now somewhere here, let's see. So classically what? Classically you measure or don't? Same on off arrangement of the lamps or not? You just simply put a box or there is no box. This is the array. Quantum mechanics says that what? If you don't measure it, these lamps are in how many states? 32 states. All zeros, 1 is 1, second is 1, third is 1, and so and so. So all 32 states. That is the major difference between quantum mechanics and classical. If you don't measure it, okay, what is the state of these lamps? 32 states. Okay, so classical mechanics says that you measure, don't measure, this is the state. But quantum mechanics says that you measure it, it will collapse into one of the states. So
You have an algorithm that makes biased.
yes, algorithm will make it biased. Okay, so now let's stop it over here. So just one thing, I will finish it over here in only one slide, because that is something from where we started our discussion. The best qubit is an atom. Best qubit is every atom or molecule. Can I make a device with this atom? Of course not. Why I cannot make a device with the atom? Because I can measure it, but I cannot put it. Okay, the location is not in my control, isn't it? I cannot manipulate it. Sometimes atom will go over there, and I put it over there. So the equivalent to atom is, I will finish it over here. So very interesting type of qubit is just last concept of the superposition. I hope all of you are familiar with the mass attached to a spring or not. So what are the possible values of x? The amplitude, infinity. If you solve the same problem by quantum mechanics, x cannot be 0. Okay, and value of the x is quantized. Mean this spring can oscillate with this amplitude or it can oscillate with this amplitude. There is a very well known problem in quantum mechanics. If you solve the mass attached to a spring by quantum mechanics, x cannot be equal to 0, mean this mass cannot be, never can be at rest, or x is quantized, can be this or it can be this. It can oscillate with both the amplitudes at the same time. Yes, it is. If I say this amplitude of vibration has 0 state and this amplitude of vibration has a 1 state, so this spring can be, okay, in both the states at the same time. What is the electrical equivalent of this? Can I have the same oscillator in electricity as well or not? LC circuit. So physics of this LC circuit is same as the physics of this one. So this is one of the most promising qubit. So this LC circuit can be in a 2 different states at the same time. This is called the artificial qubit. And it's very simple circuit or not? How many, if I want to repeat it 100 times, 1000 times, million times, I can do it or not? I can fabricate it very easily. In your mobile phone, you have how many such kind of components in your mobile phone? How many? Okay, more than 12 billion as of today. More than 12 billion. So it's very easy to fabricate. So this is the qubit in your quantum circuits. So what it is oscillating with this and this amplitude at the same time. This can be in a superposition state. You can oscillate it, you can measure it, you can use it as a qubit. Okay, so you can create the superposition state and you can process the information. Okay, so there are, yes.
These two amplitudes are arbitrary amplitudes or what?
Depending upon the spring constant and the mass, depends upon this L and C. Exactly, very good point. It is under the control of this. So when you solve this problem by quantum mechanics, you will see the amplitudes depends upon the mass and the spring constant. Over here, they depends upon L and C. L and C is in your control or not? You can make a capacitor of any capacitance. You can make an inductor of any inductance. Okay, so just if you are asking it, so when you are controlling it, generally you don't control the amplitude. How you control these, generally the systems, you control their energy or not, and this is the energy. The value of the x is quantized, energy is quantized or not. So if the oscillator is at rest, you give an energy to it, it will start oscillating. Just like as from where I started, you park the car in sunlight, they absorb the energy or not, the oscillator starts oscillating. So quantum mechanics says that they are oscillating with many different amplitudes at the same time.
How are these? They don't have any expertise in the electrical engineering, so they don't know what our circuits are, how they operate.
No, the circuit is LC circuit, I think so. This is high school knowledge, not more than that. You don't need anything more than high school. This is something I needed. So just answer a few questions. To be in a, let me conclude it, to be in a quantum computing, you don't need any background of quantum mechanics. What you need in quantum, what you need from the quantum mechanics, the states are quantized and superposition states you can create. So in physics, as a physicist, can you explain it or you accept it? If you are a computer scientist, I am asking you to accept it. You think physicists know very well about it. They also don't know anything about it. They claim they know better than you, but their knowledge is same as yours. They don't know, isn't it? So that's why to be in a quantum in the field of quantum technology or a quantum computer, you don't need the physicist. Any background of the physicist, okay, depending upon if you want to go to the hardware, you need it. Otherwise, if you are a user, you don't need it. I'm saying these words standing in a physics building, physics faculty will kill me. If you need the deep understanding, if you are working on a hardware, if you are a user, just this state. Okay, and physicists ask the physicist from where it is coming. They said that's how to explain it. I today, what's the purpose? You explain it. So for physicists, they are accepting it. More experiments are, they have more experiment to compel, to absorb it. For you, you are starting with the acceptance. So both of the you are just accepting it. So to be in a quantum computer, first thing is you have to accept systems are quantized, they can be in a superposition state, that's all. Next thing what you need, good knowledge of linear algebra, nothing, just linear algebra, okay, and some tools in linear algebra related to quantum mechanics, that's all. If you are on a communication side, cryptography, computing, information processing, sensing, anything you can do it. So you don't need, okay, very deep physics, okay, those information physicists are accepting it, you are also ready to accept. Linear algebra you need good expertise, but you are using linear algebra as a computer scientist, isn't it? In normal computer science you are using linear algebra. Linear algebra, some properties of linear algebra, okay, linear algebra is just the matrix multiplication. Yeah, every student is taking 2-8 is more than enough. 2-8 is more than enough. You have a course of 2-8 or not? Yeah, the 2-8 is more than enough. And differential equation, that much knowledge of the linear algebra is enough. Okay, if you understand what is Hermitian, what is complex conjugate, and so on. Okay, have any question? So I hope I was able to give you some idea about it. So end of the day, you need this state, that's all. Okay, so today I convince you, you are not only accepting it, physicists are also accepting it. So you, if you are going to take any course, they will start from this equation. Okay, so I give you an idea from where this equation is coming. So there are some experiment, photon is passing through 2 windows at the same time. Single photon passes through 2 windows at the same time. This is the starting point of this quantum computing. Okay, you will start from here, some tools of linear algebra, some rules of quantum mechanics, and then you are done. Yes, if you want to go to the hardware side, then definitely you need, okay, a deeper quantum mechanics. So just the one important comment is just one thing, one last thing. So I say you cannot measure the quantum state, isn't it? And I am insisting that you cannot measure it. Can you represent the quantum state mathematically? No, you are not allowed to write it mathematically as well. Let me share one slide over here. I think I have it. Yes. So this is the state, same as you flip a coin 50-50 or not. So the in quantum mechanics, the state of the coin is that 0 is head, 1 is tail. Okay. So now over here, these are the probabilities or not? So 1 over root 2 are not the probabilities. In quantum mechanics, we call it probability amplitudes. In quantum mechanics, these numbers are called probability amplitudes. What is the probability? Square of this. Is 50-50 or not? Now, how you verify this state? How you verify it? How you verify it? By observing it. How you observe it? You flip the coin 2 times, 10 times, 100 times, 1000 times. More and more, you are close to 50-50 or not? If you flip it 2 times, it's 50-50? No. First time head, second time can be head or not? If you flip it 10 times, it could be 6 and 4, isn't it? Is 60-40 or not? If you flip it 100 times, 1000 times, 10,000 times, it's 50-50 or not? Same thing, if you prepare the state, what is the way to confirm it? Prepare the state, measure it. Prepare it, measure it. Prepare it, measure it. Prepare it, measure it. Throw 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 it, measure it. Okay? Now, I know this state. Previously, I am claiming I cannot know this state. Now, this is the exact state or not? But my claim is the same state. Probability of this state and this state is same or not? What is the probability of 1? Probability of 0 is 50% or not? What's the probability of 0? 50%. What's the probability of 0? What's the probability of the 1? 50%, 50%, 50%, 50%. Measurement outcome of all of them is same or not? So you don't know the quantum state exactly, not mathematically, not experimentally. For 50-50, all these mathematical notation has same alpha square and the beta square or not? So the quantum mechanics is not giving you any clue about the quantum state. Okay, it is not experimentally. I say when you measure it, it collapses. So you don't know exactly the mathematically is. If someone is going to write down the quantum state of this one, okay, like this, like this, like this, like this, all of them are correct. Okay, so the quantum state you don't know mathematically as well as theoretically. Okay, so sometimes, so next semester I think so we are offering 471. Those who are interested, they can take this course and it will be very interesting. Basic tools, basic introduction, okay, and that particular course 471, okay, you can move in any direction. It's almost the same. 5 and it will be offered. 512 and 471. Both the courses have exactly the almost the same content. That's why you cannot take both. If you are done with 471, you cannot take the 512. But that course is based on the linear algebra and some. 512 is for MX and 471 is for the CX. But now I think so, if you are not taking the concentration, still you can take it. Only that course also you can take it. Yeah, I'm saying just for other students, those who are interested in. Okay.